Hi folks, today we're going to be talking about tries. Now, I'll note that as spring approaches and it becomes much sunnier, I have had to come up with a clever blanket over the window trick to make my face not lit so terribly, but now the wall behind me is getting really bright. So I'm going to have to get some lights soon, get real professional over here. But yeah, we're going to roll with it anyway. Okay, so enjoy the brightly lit wall behind me, and let's talk about tries. So these data structures are going to be a new type of set and map. But before we get to talking about what they are, I want to remind you about a really important dichotomy that we have in this course. That is the distinction between an abstract data type and a specific implementation. So for example, disjoint sets was an abstract data type, and we had these 4 specific implementations. And I know I've said all this like 3,000 times, but it's such an important idea that I want to make sure that it's burned into your brain. So what we're going to do today is talk about a new implementation of a set and a map that is going to be different from our hash tables or our bushy trees, but which will interact with some of our other data structures in an interesting way. And we'll see what I mean by that when we get there. So first, I want to reflect on our success with sets and maps and say we did a great job. Balanced binary search trees are awesome, or just balanced search trees in general. They give us theta, login, runtime, and hash tables also very, very good. Effectively constant runtime with some caveats. So we should maybe just say we're done and don't need to visit sets and maps again. But I do want to note that if we know something in advance about our keys, something special, sometimes we can do better. So just to give you a tiny example, imagine that we know that our keys for our sets or our map are always just a single ASCII character. So for example, I want to map the exclamation point character to 306 or whatever. Well, we can write an implementation very similar to the data index set from before that would look something like this. So I have a data index character map that stores values of some arbitrary type, say integer. Then I just have an array of v's, so if they're integers, it'll be an array of integers. And then when I put exclamation point 306, I would just go to the exclamation point element of that array and set it equal to 306. Now, what is the exclamation point value? Well, you may remember from our hashing lecture that every character in our standard character sets, it is just a number. So, for example, the letter A is just the number 97. Okay? And so what I've done here is made something just a little more general, where I assume that our data index character map has a parameter when created that determines how many possible different characters there could be. So if I want to support ASCII, I would put 128 here. If I want to support Unicode, I would have to pick some larger number. But the punchline here is that this approach is really simple and it's really fast. The runtime for this data indexed array would be constant with no caveats. Now in this case, you might argue that it's a little bit wasteful of memory, maybe, because you have all these links you may not be using. Whereas in a bushy tree or a hash table, you're going to have a structure that scales with the number of active keys, whereas here it's just it uses the same amount of memory no matter what. But I won't go there yet, but just do want to note that little fact. The key point here, though, is that by taking advantage of the special character nature of our keys, we have a simple and very fast data structure. So inspired, the special case we're going to consider and that we're going to build on is a map where where the keys are strings, or equivalently, where a set where the keys are strings. Okay, and so here, tries, their special type is that they take strings, and we're going to come up with the get and add operation as we go. Okay? I guess I should also note that we had a similar constraint for both our bushy trees and our hash tables. So for a balanced tree, our keys had to be comparable. For a hash table, they had to be hashable, though in Java that's everything. And for a data indexed array, we had characters. Okay? And so what we'll see is that tries are going to have really good performance for get and add, as well as special string operations. And so just to compare, right, we have the running example we're going to have is going to be as follows. We have a set for now, which contains SAM, SAD, SAP, SAME, A, and ALLs. And we have here the binary search tree and the hash table representation. That should seem very familiar. And in the next video, what we're going to do is see what the equivalent try will look like over here on the right.